In this video, I'm going to introduce the covariant derivative for curved surfaces and also talk about parallel transport. If you haven't done so already, I'd highly recommend you watch the previous video, video 17, which describes the covariant derivative for flat space, and a link to that video is in the description. So in the previous video, I told you that in flat space, the covariant derivative of a vector field is just the ordinary derivative, where we make sure to use the product rule to differentiate both the vector components and the basis vectors. So if we want to differentiate a vector field v, we expand the vector field out as a linear combination of basis vectors and use the product rule to take this derivative, which gives us both a component derivative term and a basis vector derivative term. And we also sometimes write this derivative like this using the Christoffel symbols, which are defined with this formula, which expands the basis vector derivatives as linear combinations of the basis vectors. And we can use similar formulas for any coordinate system that we choose. So this was the flat space definition. In this video, I'm going to cover the curved surface definition of the covariant derivative, also called the extrinsic definition. So we're going to be looking at the rates of change of vector fields on curved surfaces like the ones you see here. And we're going to be using the sphere as our main example of a surface in this video. So dealing with vector fields on curved surfaces turns out to be a lot trickier than dealing with vector fields in flat space. And I'll try to explain why that's the case. So if we look at these two vector fields in flat space, we can clearly see that the first vector field is constant because all the vector arrows have the same length and direction. And the second vector field is not constant because the vector arrows are changing length and direction. So it makes sense that the covariant derivative of the first vector field is 0, since the rate of change of the vectors is 0. And likewise, the covariant derivative of the second vector field is non-zero because the vectors are changing. So again, when I say this vector field is constant, I'm saying that all the vectors are the same. Now, I'm going to ask what might seem like a silly question. How do I know that this blue vector and this red vector are the same? How do I know for sure that these are the same vector? Well, what I can do is I can just sort of slide this red vector over here, and I can see that it overlaps perfectly with the blue vector, and that's how I know that they're the same. I slide one vector over to the other vector and compare them. Now let's consider instead a vector field that exists on the surface of this 2D sphere. So every point on the sphere has a vector associated with it. Now I'll ask the same question as before. If we have this red vector and this blue vector, how can we tell if they're the same? So you might be tempted to do the same thing we did before. Just take the red vector, slide it over to the blue vector, and see that they overlap perfectly. And using this approach, we might think, yes, the red and blue vectors are the same. But there's a problem with this method. To see why, pretend the sphere is like a planet, and imagine yourself standing here at the North Pole at the red point. What would this red vector look like to you? Well, the red vector would be pointing off towards the horizon, right? Now, if you were standing here at the blue point on the equator, what would this blue vector look like? Well, this blue vector would be pointing up toward the sky. So from the point of view of a person living on this planet, the red vector and the blue vector are not the same. One points off to the horizon and the other points up toward the sky. So if we're going to invent a derivative that makes sense for the inhabitants of this planet, we need to invent a new way of comparing vectors on the sphere that works for the people living on the sphere. So I'm going to introduce an idea called parallel transport. Parallel transport is a way of moving vectors around on a surface that sort of keeps them straight. And this is how it works. Imagine you're at the red point holding a spear. The spear represents our vector. We want to transport the spear down to the blue point. To do this, we follow the path while holding the spear as straight as possible. As we walk, the spear will always point toward the horizon. So when we parallel transport a vector, we're just moving the vector along the path, keeping the vector as straight as possible. So using the parallel transport method for moving vectors around, we would say that this red vector and this blue vector are sort of like the same vector from the point of view of a person that traveled along this path. Now, unfortunately, there is a problem with the idea of parallel transporting a vector around on a surface. To see why, imagine after parallel transporting our vector from the North Pole down to the equator, Imagine we start parallel transporting it along the equator like this. So remember, the vector is sort of like a spear or a harpoon that we're pointing to the southern horizon. So parallel transporting the spear means sort of walking sideways along this path in order to keep the spear steady, pointing in the same direction. And after that, what if we parallel transport it again, but along this curve back up toward the North Pole? So keeping the arrow steady, we'd be walking backward up until we got to the North Pole. And now you can see the problem. Supposedly, we've been keeping this arrow constant for our entire journey, but clearly this starting vector and this ending vector are different. The vector has clearly changed direction. So this shows us that parallel transport doesn't really keep a vector constant. And the reason for that is that it's impossible to define a constant vector field on a curved surface from the point of view of someone living on the curved surface. The idea of a constant vector field for a person living on this surface just doesn't really make any sense. So the idea of parallel transport is sort of the best that we can do. Parallel transport means we're keeping a vector as constant as possible as we move around step by step. The downside is that if we walk in a loop, we might notice that the vector is twisting somewhat when we compare how it started and how it ended. But this twisting behavior is just an unavoidable fact of life when living on a curved space. So when it comes to defining a constant vector field on a curved surface, the best we can do is with parallel transport and keeping a vector as constant as possible as we take small steps. So that's the basic idea behind parallel transport, but how do we describe it mathematically? Well, let's take a look at the case of a curve where this vector at the red point is parallel transported along it. If we take the first two vectors and compare them, we see that the change between them is this vector here, which points toward the center of the sphere. And if we compare these two vectors, we get this vector, which also points toward the center of the sphere. And comparing these two vectors also gives us a vector that's pointing towards the center of the sphere. So what we've shown is that when we parallel transport a vector, the rate of change of that vector always points in a direction that's normal to the surface. So recall that normal vectors always point directly out of the surface, perpendicular to the tangent plane. So when we parallel transport a vector forward, the vector's rate of change is always completely normal to the surface, so it sticks directly in or out of the surface, perpendicular to the tangent plane. So if we parallel transport this vector along this path, we end up with a vector field defined at every point on the curve. And this vector field will obey this relationship, where the rate of change of the vector field will always be some normal vector n pointing out of the surface. In other words, if we take the rate of change of the vector field and subtract the normal part, we'll always get 0. Now remember I said earlier that it's impossible to define a constant vector field on a surface. The idea doesn't really make a ton of sense. But the best that we can do for defining a constant vector field is by parallel transporting a vector along a curve. And the vector field that we get on that curve resulting from parallel transport is the closest thing that we can get to a constant vector field. And this is actually where the covariant derivative on curved surfaces comes in. The covariant derivative on curved surfaces can help us find vector fields like this, vector fields that are the result of parallel transport and are as constant as possible on a curved surface. So we're going to define the covariant derivative given by this symbol here as the derivative that gives the rate of change of a vector field v in some direction given by a vector w, with the normal component of the rate of change subtracted. So let's say we have some curve that's defined using a curve parameter lambda, where as lambda increases, we travel forward along the curve. And we have a vector field v defined along this curve. And we want to find the rate of change of the vector field as we travel along the curve. So the covariant derivative of a vector field v in a direction given by d lambda, which is basically like the direction along the curve, would be the rate of change of the vector field v in the lambda direction with the component that's normal to the surface subtracted. And remember, we said that when this quantity is 0, that's when v is being parallel transported along the curve. So when the covariant derivative is 0, that means that the vector field v is being parallel transported in the direction w. So all of this probably seems really abstract. Let's go through an example to clear things up. So we're going to be going through an example of the covariant derivative and parallel transport on a sphere whose radius is equal to 1. So in previous videos, I've talked about how we describe 2D surfaces by taking the UV plane and then putting it through a function which stretches and bends the UV plane into a surface that lives in 3D space. So each point on the UV plane gives us a vector capital R which lives in XYZ space. And for the sphere, the functions x, y, and z are given here. You can check out the tensor calculus video number 12 if you want to learn why these formulas make sense. And in this video, I'm largely going to keep this same approach for describing surfaces, except I'm going to change the variables u and v to the variables u1 and u2. So the u1 curves are the curves of longitude on the sphere that go from north to south. And the U2 curves are the curves of latitude that go from west to east. And just as a reminder, the tangent basis vectors on the sphere are given by these two partial derivatives of a position vector, which I also sometimes write as the basis vectors E1 and E2. So the E1 basis vectors are just the tangent vectors along the U1 curves, and the E2 basis vectors are just the tangent vectors along the U2 curves. So let's take the covariant derivative of some tangent vector field v on the sphere in the direction of the ui coordinate. And I'm specifically dealing with a vector field where all the vectors are tangent to the surface. It turns out that in most physics applications, we're always going to be concerned with vector fields that are tangent to the curved space. So all the vectors in the vector field v are tangent to the sphere. And remember, the covariant derivative is just the ordinary derivative with the normal component subtracted. Now, since the v vectors are always tangent to the sphere, we can always expand them as a linear combination of the E1 and E2 basis tangent vectors with these components. And we can rewrite this linear combination using Einstein notation and a summation over j like this. Now remember that we're taking the derivative of a product here, so we need to use product rule. So this derivative becomes two terms, one where we differentiate the vector field components, and one where we differentiate the basis vectors. And if you've watched my tensor calculus video number 15 on geodesics, you'll already know that we can write out this derivative of the EJ basis vector with respect to the ith coordinate as this linear combination here. So this is a linear combination of the two tangent basis vectors and the surface's normal vector. These L coefficients are called the second fundamental form, and these capital gamma coefficients are called the Christoffel symbols. So to help visualize what's going on, if this is our 3D basis consisting of two tangent basis vectors and the normal vector to the surface, and this is our derivative vector that we want to expand in a linear combination, the two Christoffel symbols tell us how much of the E1 and E2 basis vectors we need, and the second fundamental form tells us how much of the normal vector that we need. And to write this expression more compactly, I'm going to write these two terms with the Christoffel symbols using an Einstein summation over k. And now, if we substitute this into here, we get this. And I'm going to bring this term outside the parentheses to get this. Now, I actually want to factor out the basis vectors from these two terms, but notice one has index j and one has index k. So I'm just going to change this summation index here to k, because for the summation we can use any index we want, the index doesn't matter. And now I can factor out the ek basis vectors like this. Okay, so looking at this expression, all of this exists in the tangent plane because it's made of tangent basis vectors, and that means that the entire normal component of the partial derivative is here. And since we're subtracting away the normal component, these just cancel out. And so we're left with this, which is our final formula for the covariant derivative. Now, the problem here is that we don't know how to solve for the Christoffel symbols. So to do that, we're going to start with this formula for the expression of the basis vector derivatives. And remember, this normal vector is normal to the tangent plane by definition. So by definition, it's perpendicular to both the tangent basis vectors. So if we take the dot product on both sides of this formula with a tangent vector EL, then this dot product will go to 0 since n hat and EL are perpendicular. And this dot product of the basis vectors just gives us the components of the metric tensor by definition. And to get rid of the metric tensor, we know we can just use a summation with the inverse metric tensor to get a Kronecker delta, which is 1 if the indexes are the same and 0 if they're different. So if we do a summation with the inverse metric on both sides, then this would become a Kronecker delta. And this only matters when m equals k, which gives us 1. All the other summation terms would go to 0. So we can cancel out these k indexes and just write m here. And so this is our formula for the Christoffel symbols. So we finally know how to compute the covariant derivative of a vector field on a curved surface. We just use this formula here where the Christoffel symbols are defined here. So as I said before, the covariant derivative of a vector field v in some direction w is really just the ordinary derivative with the normal component subtracted. And as we just showed, the covariant derivative is also equal to this formula here. Now you might be a bit confused because in the previous video, I said that the covariant derivative is just the ordinary derivative in flat space. But now for curved surfaces, I'm saying that the covariant derivative is the ordinary derivative with the normal component subtracted. So it seems like we have two different definitions here. But if you think about it, when we're working in flat 2D space, since all the vectors live in the flat 2D plane, we're guaranteed that there's no rate of change in the normal direction. So the normal part of the rate of change of the vector field just goes to 0 anyway. So really, our definition of the covariant derivative as the rate of change of a vector field with the normal component subtracted, this definition works for both curved spaces and flat spaces. It's just that in flat space, we have the special case where the normal component of the rate of change is 0. So getting back on track, to compute the covariant derivative on the sphere, we're going to need to compute the Christoffel symbols. And to get the Christoffel symbols, we need to get the tangent basis vectors, the basis vector derivatives, and the inverse metric tensor. And I've actually done all these calculations already in Tensor Calculus video 16 on geodesics. So check that video if you want the detailed calculations. I'm just going to run through them quickly in this video. So these are the parametric formulas for the xyz coordinates of the sphere in terms of u1 and u2. And to get the tangent basis vectors for the u1 and u2 direction, we can expand these partial derivatives in terms of the xyz partial derivatives using multivariable chain rule. And computing these derivatives, we get these formulas. And we know that the metric tensor is just the matrix of dot products of the tangent basis vectors, so we can compute all these dot products and get this metric tensor matrix here. Now, given the tangent basis vectors, we can also get the derivatives of the tangent basis vectors in each coordinate direction. The derivative of the u1 basis vector in the u1 direction is this. The derivative of the u2 basis vector in the u2 direction is this. And the mixed u1, u2 derivative is this. And both of these derivatives are the same since the order of differentiation doesn't matter. Okay, so we now have the tangent basis vectors, the tangent basis vector derivatives, and the metric tensor. And given the metric tensor, we can easily get the inverse metric tensor just by taking the inverse of the matrix. So for a diagonal matrix, we just take the reciprocal of the diagonal elements. And if we recall our notation for the tangent basis vectors, which says that this partial derivative of a position vector capital R is the same thing as a basis vector, we can rewrite these formulas like this, just using the basis vector notation instead. Okay, so given all these formulas, we can calculate the 8 Christoffel symbols. And this involves working through a lot of dot products, which is very boring. But again, you can check out the Tensor Calculus video 16 if you want to see it done. So it turns out that most of these Christoffel symbols end up going to 0, and the ones that are left end up looking like this. So here we can cancel out some of the signs. And to save some space here, I'm going to use the well-known trig identity sine of 2x equals 2 times cos x sine x. And we can use that to change this into a 1/2 sine of 2x. And I'm also going to change cos of u1 over sine of u1 into 1 over tangent of u1, also known as cotangent of u1. So here we have all the Christoffel symbols. So going back to the covariant derivative formulas, there's actually 2 formulas here, one for I equals 1 and one for I equals 2. And we have implied summations over j and k here, but since so many of the Christoffel symbols are 0, we just end up with a few terms in this summation. So subbing in the formulas for the Christoffel symbols, we get this. And these are the final formulas for the covariant derivatives in the u1 and u2 directions. Okay, so now let's finally do a real example. So let's take this yellow curve on the sphere that travels along the equator from u2 equals 0 to u2 equals pi over 2. The formula for this curve is a function from the curve parameter lambda to the points with u1 equals pi over 2, which is the equator's latitude, and u2 equals lambda. So as lambda increases, we travel along the equator. And on this curve, we're going to assign a vector field, where the first component is cos of u2 and the second component is sine of u2. So at the start of the curve, where u2 equals 0, we just get the vector e1 for the vector field, which points straight downward. And we move along until we get to the end of the curve. And at the end of the curve, where u2 equals pi over 2, the vector field just gives us the vector e2, which is tangent to the equator. So normally when we take the covariant derivative along a curve parameterized by lambda, we take the covariant derivative using the direction d by d lambda. But in this case, since u2 is equal to lambda, we can take the covariant derivative in the direction of the u2 variable, and that would be the same thing. And since derivatives in the u2 direction are basically the same thing as the e2 basis vector, we can also write the covariant derivative like this, where the direction is the e2 basis vector. So given this curve and this vector field, we can take the covariant derivative. So since u1 is always equal to pi over 2, this gives us sine of pi, which is 0. And this gives us cotangent of pi over 2, which is also 0. So we're left with this very simple formula, and plugging in the first and second components of v, and then taking the derivatives, gives us this. So you can see that the covariant derivative along the equator is in fact non-zero. And that makes sense, because if you look at the tangent planes for each of these vectors, you can see that the vector is sort of spinning around in the tangent plane. So the rate of change of the vector field is not completely normal to the surface. There is a tangential part that exists in the tangent plane. So a non-zero covariant derivative makes sense. Now let's try this vector field along the same curve. In this case, the vector field is just given by the e2 basis vector. So at all points on the curve, the vector field points in the e2 direction. So I've written this vector field as a full linear combination here just to show the first and second components. And again, since u1 is always pi over 2, all of these go to 0. And since both of the components are constant, these component derivatives also go to 0. So we end up with the covariant derivative in the e2 direction being the 0 vector. And this makes sense, since if we look at the tangent planes, there's no vector change in the tangent plane. All the rates of change of the vectors are pointing in a normal direction to the spherical surface, pointing inward toward the center. And remember, since the covariant derivative is 0, we are in fact parallel transporting this vector along the curve, since a 0 covariant derivative is the condition for parallel transport. Now, so far we've been given a vector field and we've taken the covariant derivative of that vector field. And looking at the covariant derivative, we've been able to check if the vector field involves the parallel transport of a vector. Now I'd like to go in the opposite direction. Starting with a single vector and given a curve, I'd like to parallel transport the vector along the curve and get a resulting vector field. So as an example, let's try parallel transporting this vector along this curve. So in this case, our curve is the standard equator curve, and the initial starting vector is equal to the E1 basis vector. And parallel transporting this vector along the curve means requiring that the covariant derivative of the vector along the curve is equal to 0. So to do that, we start with the initial condition that the covariant derivative must be equal to 0. So we start with our standard covariant derivative formula, and again, since we're on the equator where u1 is equal to pi over 2, these two terms go to 0. And remember, we're enforcing that the covariant derivative is the 0 vector, so we get that this expression is equal to the 0 vector. And really, this means that both of these partial derivatives of the vector field components are both equal to 0. And that simply means the vector field components are equal to constants c1 and c2. So as functions of lambda, the vector components are equal to c1 and c2. And remember, we do have an initial vector which is located at lambda is equal to 0. And at lambda equals 0, we require that the vector has the components 1 and 0. So this helps us solve for the constants. We get that c1 is equal to 1 and c2 is equal to 0. So this means that the vector field components are constant everywhere. We always get 1 and 0. So that means that the vector field that results from parallel transport is equal to 1 E1 plus 0 E2. And if we visualize this vector field, we just get a vector field that's always pointing in the E1 direction. So all of these vectors along the curve are pointing downward toward the South Pole. And this is what it looks like when we parallel transport this initial vector along the curve. Now let's do a slightly less obvious example of parallel transport. We're going to take this curve where the u1 variable is equal to pi over 4. So that corresponds to this line of latitude on the sphere. And we're going to make the initial vector v0 equal to the e1 basis vector, which looks like this. And again, to get parallel transport, we have to demand that the covariant derivative of the vector field is equal to 0. So again, we start with the standard covariant derivative formula, but this time, since u1 is equal to pi over 4, when we do this substitution, we don't get the terms going away to 0. Instead, this becomes sine of pi over 2, which is 1, and this becomes cotangent of pi over 4, which is also 1. And remember, we're forcing the covariant derivative to be the 0 vector. So we end up with this final formula here, which means that this component and this component must be equal to 0. And just to make things easier to read, I'm going to replace these u2 variables with lambda, since u2 is equal to lambda. So what we have here are two coupled differential equations, and they're going to be a little bit tricky to solve, because we have v1 and v2 in both equations. Now, one trick for solving these is to take the derivative with respect to lambda of both equations. And after we do that, you'll notice that we get second derivatives with respect to lambda on the left-hand side, and first derivatives with respect to lambda on the right-hand sides. And doing some basic rearranging of terms, we can solve for the first-order derivatives with respect to lambda. So you can see now that we've actually solved for the first derivatives of lambda, and so we can sub these back into the original equations here. And the results we get are these two equations, and these are actually much easier to solve because they are decoupled differential equations. This first equation only contains v2, and this second equation only contains v1. So if you've studied differential equations, you'll know that if we take the second order derivative of a function and set it equal to some multiple of the function itself, the solutions to this differential equation are cosine and sine, where we use the square roots of these constants as the angular frequency. So if you don't really believe this, you can just try taking the second derivative of both of these functions and you'll see that it satisfies these differential equations. Okay, so we have these functions here. What we need to do now is solve for a, b, c, and d. The first step is to realize that we know the initial vector at lambda is equal to 0. So we just sub in lambda is equal to 0. And remember, sine of 0 is equal to 0, so these go away to 0. And cos of 0 is equal to 1, so these become 1. So we just get that a is equal to the first initial component, which is 1, and c is equal to the second initial component, which is 0. So we can sub these back into our original equations. Now we need to solve for b and d. And to do that, I'm going to get you to recall this first differential equation that we had. And if we sub in the first derivative of v1 and sub in v2 here, then we'll get this equation. And if we look at the initial point, lambda is equal to 0, then the sine terms will go away to 0, and the cosine term will be 1. And so given this result, we get that b is equal to 0, and we can sub that back into our original function. And using the other differential equation we had, we can sub in the derivative of v2 and set it equal to negative v1, and we get this. And this basically means that d is equal to negative the square root of 2. So we can sub that back into our equations. So finally, we have the solution for our vector field components. As we parallel transport this initial vector along the curve, we end up with this vector field, which would look like this. So as you can see, this vector sort of looks like it's twisting as we move along the path. And that might be a bit surprising to you, but remember, since this curve is not the equator, it doesn't represent a person moving forward in a straight direction. A person walking along this path is actually veering slightly toward the left. So if the person walking along this curve wants to keep the vector as straight as possible, they'll have to constantly change the angle between their feet and the direction of the vector. Another way of thinking about it is by imagining a cone that intersects the sphere along the path, like this. If you can imagine us taking a pair of scissors and cutting open the cone here, we could sort of unravel the cone and lay it flat, like this. And here in flat space, if we start parallel transporting this vector around the curve, you'll notice that the angle it makes with the curve keeps changing as we move along the curve. So it might be a little hard to wrap your head around, but in fact, this is what parallel transporting a vector along this curve looks like. Because the curve is not on a great circle, the angle that the vector makes with the path is going to constantly be changing. So this video has been going on for a long time, but I did want to mention that parallel transport keeps the vector's length the same. So if you look at this vector field and the sphere's metric tensor, and remember the formula for the length of a vector, if you churn through the math, you'll find that every vector in this vector field has length 1. And remember, this is for a line of latitude where u1 is equal to pi over 4. So parallel transport preserves the vector's length. So to summarize this video, I want you to remember it's impossible to define a constant vector field on a curved surface, and the best we can do to approximate a constant vector field is parallel transport along a curve. And this is the closest we can get to a constant vector field. And the covariant derivative is a tool that helps us find parallel transported vector fields. The covariant derivative is just the rate of change of a vector field v in some direction w with the normal component subtracted. So we can write it like this, or we can write it using the Christoffel symbol notation like this. And when the covariant derivative is 0, that means that we're parallel transporting the vector. And this formula also works for flat space. It's just that in flat space, we work with the special case where the normal component of the rate of change is equal to 0.